Hello. There are two standard ways of specifying a type system for ML. In one, the typing rules are orthogonal, in the other, the typing rules are syntax directed. In this talk, I'll advocate a third alternative based on making generalization and instantiation explicit, which is both orthogonal and syntax directed. I'll also show how this approach scales quite naturally to accommodate first-class polymorphism via a conservative extension of ML called FreezeML. Let's begin by considering three different forms of polymorphism. The ceiling notation I'm using here is taken from FreezeML. We write it to make it clear that variables are frozen in that there's no hidden implicit generalization or implicit instantiation going on. Explicit polymorphism, as in System F, requires all type and information to be written explicitly by the programmer. Implicit polymorphism, as in ML, is much more concise. If we restrict ourselves to ML polymorphism, then there's no need for the programmer to write any type information at all. Here, the type of the body of F is implicitly generalized, and the uses of F are implicitly instantiated. Semi-explicit polymorphism is just like implicit polymorphism, except we write down where generalization and instantiation take place. It's also like explicit polymorphism, except we don't write down which type variables are abstracted over, or which types a term is applied to. As it suffices to instantiate only variables, and to generalize only let bindings, we can view implicit polymorphism as just syntactic sugar for semi-explicit polymorphism. In ML, polymorphism is implicit. The orthogonal, also known as declarative or logical presentation of ML, is orthogonal in the sense that generalization and instantiation have their own rules rather than being combined with other rules. This means they can happen anywhere inside a term. At this point, I'll pause to explain the notation I'm using. I'm writing S and T for monomorphic types. I'm writing E and F for type schemas. Delta for type contexts, and gamma for term contexts. I'm using the delta because I like to be explicit about which type variables are in scope. I'm writing sigma for type substitutions. This funny looking judgment here for type substitutions says that sigma maps type variables in delta to themselves and type variables from delta prime into types over delta. The gen and inst rules are not syntax directed. M appears as both a premise and a conclusion. Now let's look at the syntax-directed, also known as algorithmic presentation of ML. It's like the orthogonal presentation, except instantiation is hardwired into the variable rule, and generalization is hardwired into the let rule. Now, an obvious way to make the orthogonal presentation syntax-directed is to add syntax for generalization and instantiation. And that's exactly what we do in explicit ML. Here and here. I'm going to make a slight refinement to the rules. Consider the identity function. It can be assigned an infinite number of types, including monomorphic types like int arrow int, its most general or principal type for all a arrow a, and generalized instantiations of the principal type, like this one. But I want to restrict its type to be the most general or principal type, and this is what this principal constraint here does. This isn't so important for explicit ML, but it does matter when we add first-class polymorphism. As I showed you earlier, we can express implicit polymorphism as syntactic sugar for explicit polymorphism. In this sense, every ML program is syntactic sugar for an explicit ML program. We instantiate each variable and generalize each let binding. This diagram shows the relationship between the systems I'll cover in the rest of the talk. The subset symbol denotes language inclusion. The languages in the top row support prenex polymorphism, where quantifiers can only appear at the top level of types and can only be instantiated with monomorphic types. The languages in the bottom row support first-class polymorphism, where quantifiers can appear anywhere and can be instantiated with any type. The languages in the left column are syntactic sugar for those in the middle column, which both subsume and elaborate into those in the right column. So ML is syntactic sugar for explicit ML, which elaborates into prenex system F. And similarly, FreezeML is syntactic sugar for explicit FreezeML, which elaborates into system F. We consciously chose to support explicit polymorphism as well as semi-explicit polymorphism in both explicit ML and explicit FreezeML. In other words, prenex system F is a sublanguage of explicit ML, and system F is a sublanguage of explicit FreezeML. FreezeML is a conservative extension of ML with support for first-class polymorphism. It was previewed at last year's ML workshop, and the FreezeML paper was published at PLDI this year. As I mentioned previously, explicit polymorphism is provided alongside semi-explicit polymorphism in explicit ML. In other words, prenex system F is a sublanguage of explicit ML. But if we do this naively, then there are two different types we can give to this term, depending on whether we take X to have type A or a fresh type B. To resolve the non-determinism and keep type inference simple, we disallow unannotated lambda and instantiation inside type abstractions by splitting the syntax into two syntactic categories, I terms and M terms. The main difference is that whereas M terms allow unannotated lambda abstractions and instantiation, I terms do not. I terms essentially consist of prenex system F plus let bindings and generalization. M terms add unannotated lambda abstractions and instantiation. Only an I term is allowed inside a type abstraction. However, inside an I term, M terms can appear in argument position and inside a generalization. This doesn't cause any ambiguity in typing, as in both cases the type of the whole expression is already uniquely determined. Now, extending explicit ML to explicit FreezeML mostly amounts to making previously monomorphic types polymorphic. I write A and B for first-class polymorphic types here. Arguments and generalization bodies now inhabit a new class of p-terms. P-terms are just like m-terms, but they are allowed to perform polymorphic instantiation, which we write p star. Polymorphic instantiation is, however, disallowed inside let bindings for reasons that I'll explain shortly. As my colleague Joe Wells proved in the 90s, type inference for system F without any type annotations is undecidable. FreezeML, in common with other extensions of ML with first-class polymorphism, works around this fundamental limitation by requiring explicit type annotations in certain places. In the case of explicit FreezeML, explicit type annotations are only ever required on lambdas. To keep type inference tractable and predictable, we restrict the inferred type of unannotated lambdas to be monomorphic. If the programmer wants to write a lambda whose function is polymorphic, then they can use an explicit type annotation. The restriction to a monomorphic argument type rules out examples like this one. The problem here is that if we naively infer types from left to right, then bad1 type checks but bad2 doesn't. In bad1 we infer a polymorphic type for f because poly takes a polymorphic function argument, and then we instantiate f to the type int arrow int. In bad2, however, we infer that f has type int arrow int and then we can't use it polymorphically. The reason for disallowing polymorphic instantiation in let bindings is that without it we run into a similar problem. In this case, the problem arises from the polymorphic instantiation of bot inside the let binding. The fundamental invariant we're actually enforcing with both of these syntactic constraints is that inferred polymorphism must never leak into the term context. Now here's the generalization rule for explicit FreezeML. G here ranges over guarded types. A guarded type is any type that does not have a top-level quantifier. Without the principal constraint, this example, bad5, type checks with f at type int arrow int, but it doesn't type check if we give it the more general type for all a arrow a. The principal constraint rules out bad5. FreezeML is a conservative extension of ML. This means we can use essentially the same syntactic sugar for implicit variable instantiation and generalizing let. The only difference is that now we instantiate variables polymorphically. We can also define syntactic sugar for type annotations on terms using typed lambda abstractions. Notice that even though the argument is a p-term, the expression as a whole is actually an i-term, which means we can use it in the body of a type abstraction, which is what we do next. We use the type annotated terms to define a syntactic sugar for a typed form of generalization. And correspondingly, we can use this syntactic sugar to define a type annotated form of generalizing let. And this is a feature of FreezeML which allows quantifiers to be reordered or discarded, for instance. We can also define syntactic sugar for non-generalizing let bindings. The unannotated variant here ensures that even if we bind a p-term, which isn't normally allowed by a let binding, it cannot instantiate any variables polymorphically. The generalizing and non-generalizing let bindings together can be combined to implement the value restriction. Explicit FreezeML supports quite natural equational reasoning principles. Our notion of equivalence is only defined when both sides have the same type in the same context. The equational rules for the system F fragment are standard beta and eta rules. The other rules here describe how to elaborate the other parts of FreezeML into system F. The types are filled in using the typing derivation. Let is just equivalent to an applied lambda. Unannotated lambda is equivalent to annotated lambda. Generalization is equivalent to type abstraction, and instantiation is equivalent to type application. This work highlights several general properties to strive for when designing typed programming languages. All of these properties are really about making the typing of programs more predictable in order to make it easier to read, write and reason about programs. In this vein, we encourage language designers to express implicit features such as generalization and instantiation as syntactic sugar. I'd like to finish up by advertising our ongoing work on FreezeML. You can read the PLDI paper here and see Frank's talk here. We're currently working on an AGDA mechanization of explicit FreezeML. Initially, we built this just to validate that the typing rules with the principal constraint are well-founded. As explained in the PLDI paper, we do so by indexing the judgments by untyped terms. We'd now like to mechanize other aspects of the system, including type inference. We also plan to extend FreezeML to support type functions as in f-omega, bidirectional type systems, and general typing constraints as in HMX or qualified type systems. Thank you for your attention.